Not sure. So let's system.out.println r, yes, right? So now we go back to a last part, which is read it out loud, public static void main string args, sure. Int n is equal to 3, int res is equal to factorial of n, semicolon, yes, system.out.println res, public static int fact of int n, if n less than or equal to 0, return 1, return n star factorial of n. Yeah, looks good. Let's see. Again, no one ever writes clean code in the first go. Let's give it 5. Okay, that's correct, because 5 times 4 is 20, 25, 4, 3. 20 times 3 is 60, 60 times 2 is 120. So the answer is correct. And tada, we have our first recursion function. So I know this looks pretty simple, but this is very powerful. And the reason is now you can actually do this iteratively also, right? So let's say we do this iteratively. Let's call it public static. Oh, before we do that, I'll tell you why the reason I was insisting on using Java while you're practicing. Let's say you switch to Python, right? And let's create a new project, new site. When it comes to Python, you will realize, oh my God, it's so easy and so simple that you don't have to worry about main, you don't have to worry about anything else. You can start writing factorial. You don't have to worry about int n. It actually feels better. But the fact is, when you're writing def fact n, you should remember that you're already thinking about int n, and what your return is going to be. And when you write factorial, what did we do first time? Return n star fact of n minus 1 if n less than or equal to 1. I'm probably going to screw up the syntax this way. I think return 1. That's it, right? See, I'm putting semicolon, but that's switching between two languages does that too. So now you have to do fact of 5, and that's it. So you can sure run this whole thing. Hello world, great, it printed. Hello world. Let's print fact of 5. It already printed 120. So in short, by the time you get to Python, in that 80% of your learning process, your brain has slowly understood the fact, or you have created new neural pathways to think about what is the input, what is the output, what should be my return, etc., etc. And once you're that comfortable with Java, I'm not even trying to teach you Java. I'm just saying your thought process has to be like Java so that you can think of the inputs and outputs. And even here, you don't have to be confused. What am I returning? What should I be doing? Because you already thought of all this here in Java. Okay, with me so far? Now I am going to switch back to my screen sharing in the iPad. How many PhDs do you need to run an iPad? All right, host as disabled. Okay. So now, this is how we are slowly going to build up our foundations. We saw factorial. We saw two ways of writing it. One is recursion, and we haven't seen the iteration yet, right? I'll just write it out. So iteration, let's go. There's two ways of iteration. So remember, we are starting with the complex thing. We are starting with Java. We are starting with recursion, but we're also going eventually to Python or eventually to iteration. When you write it iteratively, it'll simply be public static void int, again, void, let's see. Where's my pencil? Where's my pencil? Where's my pencil? Here, void fact, different color, doesn't matter, int n. And now all you can do is a for loop, which is for int It's all going slanting. Int I is equal to 0, I less than n, I is equal to 1, because you don't have to go all the way to 0. I is equal to 1, I less than n, I plus plus. This is just why I was saying use an eraser. Your brain is, don't want to mess with your brain. Eraser, not erasing that, very helpful. Okay, just say int I is equal to 1. All right, okay. I'm screwing up the colors on me. Okay, so int I is equal to 1, that's called int fact is 1, fact equals fact star I. So this is also pretty simple, and at the end you can just return fact. So my question then is, if the same problem can be written recursively and iteratively, the question is, which one is better? Which one is better in terms of time complexity and space complexity? Which one do you think is better? Question to you. Take a guess. Between recursion and iteration, which one do you think is better for time? And which one do you think is better for space? Anybody? Okay, any comments? Take a random guess. It's only half 50-50 chance.
Recursion is better.
Recursion is better, okay. For both time and space?
Sure.
Okay, sure. Now, iteration. Now, so this is one of the questions an interviewer will always ask you. You wrote up something, he's going to ask, what is the time and space complexity? Especially if the question is like a recursion, it's definitely going to ask you that. To understand what the time complexity is, people tend to like memorize things like, oh, if it's 2 for loops, I'm going to say order of n squared, and things like that. But even to understand that, you have to go one level deeper into what we call as a memory model. Memory model of anything, right? So when we were in C, we were simply using the memory model of the original designers of the von Neumann architecture. C++ did the same thing. Java came up with JVM, which has its own memory model. And this is how it looks like. Or this is how deep inside our computer works in the RAM. There are 4 areas to your RAM. The first one is called your text area. Second one is your data area. Then this whole thing is called a heap. And this whole thing is called a stack. So if you have heard these words before, stack is something where we have a data structure. This has got nothing to do with the data structure, but it so happens that stack is implemented as a data structure where you have the last in, first out. And why are we doing it this way? So whenever you call a function, the first thing that happens is there is a fixed stack frame that's created for the main. Okay, so what was our function here, which is main? Let's see, go back, and we don't have a main anywhere, but okay, let's add a main too, right? So remember in the online GDB, we were saying, let's write in Java for now, public static void main string args. And let's say you have int n is equal to 3, and you're calling result int result equal to factorial of n. And you have print. Or in this case, system.out.println if it's Java, and you print rest. So the moment you write this code, or more importantly, the moment the compiler gets here, what it first does is it takes your stack frame and takes your memory and allocates a stack frame. And the definition of stack frame is a fixed memory of size k. Now, the moment it allocates stack memory, what it is going to do now is it looks at int n is equal to 3. Okay. The first thing all these programming languages ask is the value I'm dealing with a primitive data type or not? So if it's a primitive data type, like int, char, what it'll do is it'll take the stack memory and allocate a slice of the memory there. Depending on your compiler, usually int might be 4 bytes or 8 bytes, depending on the kind of compiler you're using. But you're saying int x is equal to 3 is created there. Then you encounter int res equals fact of n. Okay, so it initializes int res and it looks for, oh, fact. It looks around and it realizes, oh, fact is another function which we had created here. Let's say we are doing it recursively, right? This is another function. So every time the machine encounters a new function, it creates a new stack frame, pauses everything it is doing in the stack, leaves it in the stack, creates a new stack frame, and for the function fact. Okay, and what happens inside fact is, let's go back to do and see what happens inside fact, right? So you have fact n. First thing is if n less than or equal to 1, return something. So usually when you get into a function, you have to think of it in terms of the original assembly language instructions that might fire here. So here, bad color, one, this, like this is the first instruction. So instruction, let's call it T1. T1 is here, and T1 is the first instruction that the compiler has to do. With me so far? Now, here is T2, which is, it has to look for a check, T2. Here it is T3, here is return 1. Now it has to multiply something, so take the value of n, multiply it, then hand it over to another function, child, T5, right? So what happens is when the compiler is executing, it does T1, T2, T3, T4, and it says, oh, we are calling fact again. So what do you think it'll do? So here we have n. Let's say we are passing n is equal to 4, right? What are we passing? Sorry. What did we decide? Int n is equal to 3. So not x, that's n. So let's see. Int n is equal to 4, and we are passing n's value is 4 here. So what do you think the factorial will do when it says fact of n minus 1? Fact of 3. What do you think it will do? Okay. What the machine will do is create another stack frame of size k for factorial function again, and you give it 3. So this is actually going to be here. So remember, each of these stack frames cost you k, k, k. And so on and so forth, you will end up with, until you hit 1, you keep adding stack frames. Now, the reason I'm talking about all this is, if you simply think about it in terms of memory usage, you can see that every time this function is called inside, again and again and again, we are creating a new memory frame. So let's say here the factorial is 3, so it goes to 3. Right now you go to 2, you go to 1. I'm writing into the heap, but just imagine all this is stack. And now you start returning. You return 1, you return 2 times 1, you return 3 times 2, and you return 4 times 6. It has to go all the way back here. And every time a stack frame returns, the memory just erases it. So the first point is, recursively, we are creating n times k memory every single time. Right? So let's go back to where we wrote the recursively space complexity. We are creating order of n dot k. Now, time complexity. when we talk about time, let's say, where did we go? The T1, T2 stuff. Okay, so here, there are 5 instructions within this function itself. Let's here in this case 5. And remember, all these 5 ones are going to be executed n times. So this is 5 times n. So every function is being executed 5 times. So your space complexity is another constant factor, k times n, right? Sorry, time complexity. Okay. Now let's look at the iterative part of it. If you look at the iterative part of it just plainly from a space perspective, this is how it looks like in the machine. We come here, the machine has a main, creates a stack. Now it says fact. Okay, it creates another stack for fact. In the stack, it initializes fact is equal to 1. Okay, it initializes another variable I is equal to 1. And the third, so there are only 3 operations here. Int, initialize this here, and multiply it with fact and return it. Now, all that happens inside the same stack frame, because remember, a new stack frame is created only when we call a function by itself. We are not calling a function, we are iteratively sitting inside these values. So all this is what we call constant memory, or in this case, we are not going on multiplying in terms of factorial of 4, factorial of 3, factorial of 2, factorial of 1. We are in fact using what we call order of 1 memory. Now, time complexity wise, you can see that iteratively, again, remember, we are doing this only once. Let's say we have T5 elements there, right? So T1, T2, T3, T4, T5, we are doing this in order of, in this case, 5 times n. Or in this, so essentially my point is, this value is not, it's not variable, it's limited, because we are calling the whole thing only once, the whole function. So long story short, iteration is always better in terms of time complexity. So then let me give you an example. Let's say we have the n is 10 power 5. We are basically telling you, give me the factorial of 10,000, maybe one more, 1, 2, 3, 4, 5. All right, 100,000, right? And then let's say in the code, we have 5 of these values, 5 of these instructions every time. So what happens is, in terms of time complexity, another pencil color. So your one color. Your space complexity in terms of recursion is n times k, which is 5 times 10 power 5. Let's say there are k is also like 5 times 10 power 2 instructions. So it's 10 power 2 times 5, that's equal to 10 power 7. Recursion, on the other hand, is order of 1. Time complexity wise, this is again 10 power 7, because k dot n. And here it's 5 times 10 power 7, 10 power 5. So you see the difference here. It's at least a couple of tens powers higher that we need for recursion, both space and time. Despite all this, why am I insisting we should learn recursion first? It's exactly for this thought process. This is opening your mind into the idea that do not memorize anything, but think of any time and space complexity in terms of stack frame. You might not see the purpose of this. Eventually, when we get into complex problems, you will realize, oh, you don't have to memorize anything. You just have to think of it in terms of fact. And another very interesting reason why I'm teaching you the memory model is pointers. Now you will think, oh, pointers is such a C-based concept, right? That's not true. The core idea in C was transferred to all the languages so far. In C, let's say you have int x is equal to 5, and you say int star y is the address of x. right? So what happens is, remember the same idea, stack. We have a heap here, and we have this other stuff here on top. So every time you create x is equal to 5, it's created here. Y is another label which holds the address of 5. But in C, they insisted that any of the complex data types should always be allocated on heap. Say, for example, if you have a string n is equal to name, the actual memory of name happens in heap, and n, just the label stands here as the pointer. So why am I telling you all this? The later languages, they just took all this stuff, glorified it, and simply said, oh, let's still initialize everything fundamental in the stack. Int x is equal to 5 is in the stack, char y is equal to a is in the stack. But the moment you say slightly more complex things like uppercase string in Java, it is a class. And what exactly happens is it's a complex data type, and they allocate a memory in heap. So now here when you say string n is equal to name, your actual value name sits here, and just the pointer s sits in stack. Now so this is a very fundamental concept. So your object is really sitting in the heap. And how does that help? It helps because of two reasons. One, so if you talk about just the memory alone between stack and heap, stack, heap, what happens if you remember is every time a stack is allocated, when you call a new function, or more importantly, the memory it creates like this is erased every time the control is sent back. So we are not retaining anything in memory. In heap, the memory is not going to be erased as long as something is pointing to it. So for example, if you had a function and you are creating string s is equal to name here, the moment you return it, this value vanishes, because you can probably say s is pointing to something in the second stack, but it's not there anymore. It's called a dangling pointer. So that's what we call your memory overflow and things like that. However, on the other hand, if this s was actually pointing to something in the heap, it's going to remain there even after the control gets passed to your original main function. And the reason I'm saying this is, next we will see, let's say, linked list, right? So I'm not even getting into the complex memory model for Java, but just imagine I want to create a linked list. Will you create it in stack or heap? Just given the fact that the heap memory is not erased and stack memory is immediately erased. Should make a caveat there, heap memory is erased if nobody is using it. For example, you allocated the name here, and after the function executed, you realize, oh, I don't want the name anymore. I'm not going to call name anymore, or even assume that your function finished execution. So still, this name blob is going to remain in memory until something known as garbage collector comes across. And garbage collector is, let's say, it happens on a timer, happens only every 5 minutes. Until then, including the execution of your code, the data is going to remain in the heap. So having said that, let's say I'm creating a linked list. So you don't even have to know what a linked list is as of now. Linked list is nothing, an abstract concept where you say, hey, I have 3 blocks, 3, 4, 5. If I want these a linked memory like this, would you create it on a heap or a stack? Take a guess. Take a
Maybe,
guess. Sorry?
maybe hit.
I didn't hear it. Sorry, can you say that again?
Heap.
Heap. Why?
Because it's a complex data type and it won't be erased.
Perfect. Yes, that is the answer. Not just because complex data types, I want in a stack, if I wanted to allocate it, it would have to be contiguous, and getting a contiguous set of memory is difficult everywhere. But more importantly, if you create it in stack heap, you don't have them to be contiguous. All you have to remember, you as in the control execution person has to remember is, I have a pointer 1 pointing to 3, and it also has another pointer internally, which is the next pointer. So if you know how linked list is originally written, it's just a class node int data and node again next. What does this mean? This means there are 2 pointers. There is a data pointer, which is pointing to the value 3, the memory location. Another pointer next, which is pointing to my next value. So all your complex things, the things that need more memory, is allocated on the heap. And all we are storing in stack is minimal data, because stack is limited. Remember, they are reusing stack and they're erasing stack. So stack is very costly. So now you just keep the pointers here. More importantly, what I want you to remember is, let's call it node, and it has a constructor here. And the constructor is simply, if somebody is passing you int x, and you are saying this dot data equals x, and this dot next equals null. So this is how a basic node is created. Now, inside your main, what you will do is you will be saying node, something of node type h, is equal to new node of int 5. So when the moment we call this is the keyword I want you to remember, new. If you anything new is going to be on heap. Remember, I was telling you the fundamental data types, difference between fundamental and complex data type. In complex data types, if you go back to the original C, even if you had a string, what they will do is something that you're creating on the fly is called calyx or malloc. So anything that was created on the fly, you had to allocate memory on the fly. So you need a bunch of garbage memory that you can play with, not of fixed size. That is where they would say, okay, let's throw that in heap. We have things to play there. As time passed from C, C++, we went to Java and Python. They took the same calloc malloc and called it nothing but new. So why am I insisting this? Because once this idea is completely clear in your head, you will never run back into problems like, let's say you have a node temp is equal to h. So if while writing your code, if you suddenly thought, wait, is node a copy of h or is it a pointer? So now, remember, we are not using the new keyword. So which means you can assure that your temp is just a pointer sitting here. And if the h, let's say h was, yeah, all right, there goes my technical skills. H was originally pointing to the head here. What did we call it? N x is equal to 5. Let's, for disambiguation, let's call it n is equal to 3. Right? So we're calling h for the first time. H is pointing there. Now, when you say temp equals to h, all you're doing is creating another point to 3. Now, h can go to h dot next, but temp is still going to keep pointing to 3. That's very important. So then once you get this idea fundamentally, a lot of these class object things will easily come into your head. Or even when you're writing linked list, you will not fall into the trap of, should I move h is equal to h dot next? Will temp move And the whole reason I'm trying to teach in this class is not memorize, but always go back to the basics. If you understand just these few concepts I told you today, that will help you a lot in when you start writing your own code. Remember, the goal is to make you love it foundationally up like a triangle so that you love the whole idea instead of memorizing. That's when you have to memorize 7,000 problems. But more importantly, if you memorize, your brain is like a stack. There's a limited memory, and it cannot remember all the 7,000 problems, but it's going to start panicking because you miss one of the 7,000, your whole castle of cards is going to come falling down. Meanwhile, if you can always go back to the foundation and start thinking, oh, this is why. Oh, this is why it should be h dot next. Then every line you will be fundamentally looking into this core idea. So let me give you an example here. So I know I very subtly I introduced linked list here. So recursion, by the way, I want you guys to go to Geeks for Geeks, search for recursion. There will be 3 types of problems: easy, medium, hard. Your homework is finish all the easy ones yourself. Homework, just finish the easy ones first. And when I say finish, remember, every time you encounter a problem, there are 2 options. Either you have seen it, or you know it, or you can try it out, or it's a new problem. Try this for 5 minutes, which is just phases of including your paraphrase and logic. If you're confident your logic is good, go ahead. Write the code, think of edge cases. But this is, let's say, overall, you should take only 10 minutes for this. Don't worry, you might not in the first phase. More importantly, keep a 5-minute timer when you start looking at a new question. If the timer goes and you still haven't reached the logic stage or you're not confident, it's okay. It's okay to fail. It's very important you look at the solution given there, read and understand the solution yourself for 5 minutes, close the solution. You have to literally shut down your monitor or even like put another window if you know your brain can completely zone out of it. Once you close that solution, write it in pen and paper for 5 minutes and code it up in 5 minutes. So your new question is done in 15 minutes. In fact, if you want, you can store it, add this into your notebook, or if you go to online GDB, I have like a collection of all the problems I have solved. It's all kept there, and that's my online notebook, right? The review notebook. So the reason is this is your homework. Go to recursion, do that. Let me see. Screen, continue, go back to the sky, online GDB. So as time progresses, you will start building up your code base here, right? This problem, next problem. And more importantly, these are problems you solved or did on your own after looking at the solution. This is the same idea of using a notebook. And the idea is every day, open up this list of your files and think about this problem. Oh, champagne overflowing glass problem. Give it 2 minutes. How did I do that? Okay, I think this is how you do it. So just click on it or look at the solution. Oh, that's it. Okay, you're right, you're wrong, but revise this every day. You're slowly going to build up these almost 7,000 questions yourself if you get there. But it's very important you look at it every day for 5 minutes. Just all of it, just browse through it. Okay, this one, maybe even randomly pick a few. Oh, how did I do this one? Okay, it's recursion. Oh, it's a linked list. Okay, I do it this. So you see what I'm doing here, right? I'm building you a couple of foundations in recursion to start with a memory model, which will eventually help you answer your own confusions. Okay, I think I'll stop here. We are almost out of time.